So the talk is about, yeah. It's about problems in Ramsey-Turán theory. So to motivate this theory, let's start with some basics in extremal graph theory. So so at any point, if anything is unclear, please stop me. Right. So let's start with the classical problem. In extremal graph theory, this is the Turán type problem. So basically, we say that the problem is you fix a universe of n vertex graphs. They're all sharing one same property. The property is they don't contain some small subgraph H. They don't contain a small graph as a subgraph. Then what you want to do is you want to maximize the number of edges within this class of graphs. Okay. So this is the Turán type problem. What is the maximum number of edges among this class? So okay. So we define this. This is all clear. So we define extremal number of H is the maximal number of edges in an n vertex graph G that is H free. Okay. So one of the earliest such a result is Mantel's theorem, later generalized by Turán, which says if the forbidden graph is clique, say kr plus 1, then the best you can do is by looking at this, so nowadays called R-partite Turán graph. I will denote by T sub R of n. So what we do is we partition the vertex into R almost equal parts. So each one of these is roughly n over R plus minus 1. We leave each part independent. So there's no edges inside. And we add all the edges across. Okay, so this is our graph. And obviously there's no clique of order K R plus 1 because I pigeonhole this R plus R part. If you have a clique, then you will have two vertices falling into the same part. And so basically their theorem is saying that the maximum size is achieved by this graph. And this is a unique maximizer. So then the next step after seeing this result is what if we forbid the generic graph, right? Not the clique. The clique is a very special one. And the far-reaching extension by Erdős and Stone, I think in the 40s. So what they prove is that they basically determine the asymptotic, we find the asymptotic solution for this Turán type problem for any non-bipartite forbidden graph H. And they show that this is determined by another important graph parameter, the chromatic number of the graph H. So what they prove is the extremal number equals to up to an error term this function. Can you see down here? Oh, right. Okay, so we have this general, I will just use this side. Okay, we have this solution. So let's first see the lower bound. It's very easy. The lower bound, because if I just take the Turán graph on chi of h minus 1 part on n vertices, then this graph has that many number of edges, and you cannot have a copy of h, because if you can embed h in here, the quadratic number of h will be one smaller than it should be. So that's a contradiction. So lower bound is very easy. The upper bound is also not so hard. One can prove it. Okay, so now, after seeing this result, this is a remark. This basically resolves the Turán problem for all non-bipartite h, because when h is bipartite, then the leading constant there, 1 minus 1 over 2 minus 1, becomes 0, telling you only the information that the graph has 0 edge density, right? But in fact, yeah, for bipartite h, it only gives a bound that looks like this, which is not very informatic, because there's another result saying that no matter which bipartite graph you forbid, it's always polynomially smaller than quadratic. So there always exists constant c such that the number is big O of n to the 2 minus c. Determining the bipartite Turán problem is difficult, but this is not the focus of today's talk. Today's talk is about Ramsey-Turán theory. So how does it come in? I think in 1969, Schorsch started this type of problem. Basically, she observed that if we look at this extremal graph, for example, here, this unique extremal graph. So, okay, before that, how do we come up with a problem? We say that, what is Turán type problem? We say that we fix a universe, which is the h-free graph universe, and we fix a parameter, which is the size of the graph, the number of edges. Then the problem is to maximize or minimize this parameter. So in this particular case, we want to maximize the number of edges. Once this problem is solved, then you ask, you know the value, then you ask for the structure. What about the extremal structure? And in this case, we also know the extremal structure. There's a unique one here. Now, after this, it seems like the problem is solved, but you can ask more, right? If the extremal structure has very rigid structure, then we want to ask, what if we forbid this rigid structure? Can we improve the bound? This is the motivation. So she noticed that in Turán graph, there is a omega linear size independent sets. So this is one way to measure that this graph is very rigid, right? Because generally, if you take a random graph, the linear independence number cannot be linear. So what if we forbid this obvious thing in the extremal structure? We say that now we also consider h-free graphs, but in addition, we require its independence number to be sublinear. How about the number of edges now? How many you can get? Okay. To warm up, I haven't defined you. So let's start with the definition. So the definition is RT stands for Ramsey-Turán. I have N, I have H, and the additional parameter F, M, which bounds the independence number. So this is the maximum number of edges in G, where this G satisfies, I have n vertices, I'm H-free, and the independence number is at most m. Okay? So you see, the only difference here is this additional constraint on the independence number, right? Such type of problem, I mean, if you look at it, this kind of problem appears everywhere, maybe not in the name of Ramsey-Turán. There are a lot of extremal type problem. They look at the extremal structure and they forbid the obvious thing there, right? And they say that, can you improve the bound? So, okay, but there's an immediate problem now about this definition. Can any one of you see it? The thing is, in the Turán problem, we usually take n goes to infinity, right? We imagine n to be a huge number. So we look at the asymptotic with respect to n. Here, one observation is, it's only meaningful if m is a function of n. Because by Ramsey theory, if m is a fixed constant when n goes to infinity, either your graph has to have a clique, which obviously contains h, or the complement contains a clique of size m. Then you get an independent set of size m. So we have to take m as a function of n. So the most classical case is to consider the case when m as a function of n is sublinear, little o of n. Okay? Which is precisely how we studied at the first place. We have in the Turán graph an independent set that's linear. Now we forbid that. To get a feeling, let's do this exercise together. We know that by Mantel's theorem, this is n squared over 4 because of this graph, Turán graph on two parts, right? N squared over 4. It has positive edge density equal to 1/4. Let's say I normalize by n squared instead of n choose 2. Now what if we add this additional one? So now I write the Ramsey-Turán number for triangle where I forbid linear size independent sets. Anyone? How many edges? It's not so hard to see that now it has 0 edge density, little o n squared. So suddenly you drop from positive edge density to 0 edge density. Why? Let's pick in this graph G. So how do we prove an upper bound? You start with the G, okay? I say that the G is triangle free. Independence number is little o n. I want to give an upper bound on the number of edges, right? N vertex graph. I pick such G, I look at the vertex. The neighborhood of this vertex, because G is triangle free, this is independent set. Okay? Any edge in the neighborhood will result in a triangle. So that means the degree of the vertex is bounded from above by the independence number. Okay? So the maximum degree of the graph is always at most independence number, which is little o n, because this is triangle free. Okay? So if the maximum degree is little o n, then total number of edges is little o n squared. So already we see a difference here, the effect of forbidding the linear size independent sets. Any questions? So the first major open problem in this area is to get the analog of Erdos-Stone in Ramsey-Turán contact. This is open. So can you find some parameter that is like chromatic number in Erdos-Stone theorem that determines asymptotically the Ramsey-Turán number of H when you forbid linear size independent sets? Okay, this is not known. Let me put a quote here. Erdos-Stone theorem Okay, this is open. So we see that here, triangle is really easy. We get 0. But already, we don't know this case. So if you're bored in the rest of the talk, you can try this problem. What about the blow up of the triangle, where each vertex is replaced by 2 vertices? So this number, so this looks like this. Okay, the blow up means initially I have a triangle. Now I replace every vertex by an independent set of size 2. Then I replace every edge by a complete bipartite graph. Okay? So for this graph, it's not known whether this is dense or not. We know that it's bounded from above by n squared over 4. And the lower bound we don't know. We don't have lower bound. So one of the question is, is this little o of n squared? Okay? This is not known. So what does this mean? If you want to prove it, you have to show that if you have a dense graph, if you have a graph with positive edge density, sublinear independence number, then for sure you can embed the copy of K222 if you want to prove it. If you want to disprove it, you need to construct the graph with positive edge density, does not have K222, and sublinear independence number. So either way, either you improve this or get some dense lower bound. There's no progress now. So the edge density between 0 and 1/4. So this very simple case already shows that getting an Ehrlich-Stone type theorem for this Ramsey-Turán theory seems quite difficult. Okay. Right. So what about, okay, we talk about general graph here. That's difficult. What about cliques? The first thing you think about is forbidden clique, right? So for clique, at least we know what's going on. So let's see. Continuing what's known. So before that, I need to give a formal definition because so far, this little on is not quite formal. I just say it's sublinear. What's the quantifier? So let me give you the formal definition. We define, okay, it's the Ramsey-Turán density of a graph H, delta, so we first define this Ramsey-Turán density, rho of H delta. So what is it? We look at the Ramsey-Turán number of H when the independence number is bounded from above by delta n for some delta between 0 and 1, normalized by n squared when n goes to infinity. By an averaging argument, you can show that this limit exists. Then the Ramsey-Turán density is defined to be, now I take delta goes to 0. Okay? This is what I mean by little on. I take delta goes to 0. Then I can formally define so this formally they define it to be, okay, up to an error term is this Ramsey-Turán density times n squared. That's how we define it formally. So this is just how to write it precisely, but we've already do the exercise here. So the next step, what about K4, right? It's known there. So in fact, right, K4. Turns out next step is already quite difficult. The Ramsey-Turán number for K4. So for the upper bound, I will directly just write this. Okay, rho of K4 is at most 1 over 8. So this is saying RT of n K4 little o n is at most n squared over 8 plus little o n squared. Same thing. I use this shorthand. This is normalized by n squared. So before, this exercise shows that rho of K3 equal to 0, right? This is 0 density compared to the normal Turán problem where you have 1/4 density. So this is proved by Semmeredy, one of the first application of Semmeredy's regularity lemma. This is by Semmeredy. In 1972. Okay. Well, if you see the proof, it's not so hard, but the lower bound for quite a while is not known that whether this is 0 or not. Is it positive? No one knows. Because if you think about it, how can we construct the graph that's K4 free, sublinear independence number, and dense? It's quite difficult because look here, if you want to make these two, we know that K3 is 0 density. If you want to have positive edge density, you have to add some edges inside. When you add edges on both sides, you get K4. It's easy to get K4. Okay, so it's not so easy to come up with this construction. Finally, the K4 problem was resolved by Bollobas-Erdos by an ingenious construction. So this is 1976. They provide the matching lower bound. Okay, so at the end, this Ramsey-Turán density for K4 is 1 over 8. So let's take a look at this very nice construction informally. So I will not provide the details informally. So what we're gonna do, we need to construct n vertex graph G that's K4 free, independence number sublinear, edge density roughly n squared over 8. Okay, this is what we're gonna do. So basically, the construction utilizes the high-dimensional sphere. So what's the property of high-dimensional sphere is that imagine pole sets, all subset of n, all the measure concentrated in the middle, right? Every middle layer is roughly 1 over root n measure. So with that being said, what it means is that if you just take a tiny strip around the equator of the high-dimensional sphere, most of the measure are there. So how do we utilize this fact? The construction start with, it's a almost bipartite graph. So let's say the vertex set G consists of U1, U2. This is my U1. This is my U2. Inside here is the same graph. So this is inner graph, cross edges. Let's first describe the inner graph. These two are isomorphic. For the inner graph, it's called Borsuk graph. I think it's better if I write there, right? These two. Can you see down here? It's okay. Okay, so how do we construct this very nice construction? We have to first introduce what's inside. What's inside is called Warwick graph. Okay. The property of this graph is that it has high odd girth. In particular, it's triangle free. Okay, you can have short even cycle, but you don't have short odd cycle. You don't have C3, C5, C7. Another property is that independence number of this Borsal graph, let's say B, is little o(n). Okay, because we want to make the graph to have sublinear independence number, so right? So we want to stick in inside. We need to make sure no matter which linear size subset you're looking at, the independence number is sublinear. So if you make sure this is sublinear, we are happy with the requirement on the independence number. Good. How do we do that? Let's draw the Borsal graph, the vertex set, as a high dimensional sphere. You put the n vertices uniformly distributed. You make them uniformly distributed on this high dimensional sphere. You connect 2 points as an edge if they almost antipodal. Okay? So this point is adjacent to all the points that's almost on the other side. Okay? So immediately we see the first property, high odd girth. Because how the cycles, if you have an edge, you can only bounce around like this. Maybe you change a little bit over time. You can never get a short odd cycle. Does it make sense? But why independence number is little o(n)? As I said, that use the concentration of measure for high dimensional sphere. Okay, first of all, again, I have two vertices, V1, V2. V1 is adjacent to V2 in Borsal graph if and only if, let's say, their distance for V1, V2 is bigger than 2 minus some epsilon. Okay? So they are very, very far apart, almost in the antipodal position. Okay, so this immediately implies the first property. What about the second property? You have to use the isoparametric inequality, which says that if you fix the measure, then the spherical cap minimizes the diameter of this area. Okay? One of the property, isoparametric, okay, it says because if you're given the area, you want to close a land to do the farming, right? You want to reduce the number of material you used for the fence. You want to make it as like this as possible, right? It holds in a high dimensional too. So now I give a proof informally why independence number is sublinear. If you take any linear size set, you take what do I want to prove? Linear size set contains an edge, right? Independence number is sublinear. If you take a vertex set of size big omega of n, linear size, then by the isoparametric, your diameter is close to 2. Because most of the measure concentrated in the middle. So in that case, you for sure can find 2 points that are antipodal. Then you contain an edge. Let me write it down. Okay, so now I need to prove that this graph is this. So how do I prove? take a vertex subset, let's say capital W, linear size, okay? So this is my Borsuk graph. You take some W, something like this, on the high dimensional sphere. What do I know about high dimensional sphere? I draw another copy here. If you take a spherical cap where the diameter is less than 2 minus some other epsilon prime, as long as epsilon prime is not so small, the measure tends to 0, right? If you step away from the equator, it decreases drastically. Just imagine the discrete version, the hypercube. With that being said, if you take a W that has positive measure, this has measure tending to 0. If you take a subset that has positive measure, that means the diameter is as big as the spherical cap. That means you can find 2 points. They are almost antipodal. Then you have an edge. Okay, informal proof. Now, this is not yet. The genius part comes now. How do we put together these two graphs and get n squared over 8 edges? What we do now is, it's very nice. We have 2 copies of Borsuk graph. We imagine them on the same high dimensional sphere. How do we put the cross edge? You put the cross edge, if this point is in the hemisphere of center at this point. So for the cross edges, so this is my V1, which is here. Okay, I have my U1 here on the other side. V1 is adjacent to U1. If on the hemisphere, if you put them on the same high dimensional sphere, U1 is sitting in the hemisphere center and P1. Okay, then you put an edge. Now I ask you, what is the degree of every vertex? Roughly half. Because with probability half, U1 is in the hemisphere center at V1, right? Very roughly. So you have density 1/2 going across. That's how you get n squared over 8. But why it has no K4? Let's draw a picture. It has no K4 because how does the graph look like? You have these 2 Borsuk graph, right? If you have a K4, for sure you cannot have a triangle here and vertex here. Because we know Borsuk graph has high outgirth. You have no triangle. So that means you have to have 2 points on each side, right? But if you have 2 points on each side, let's see the geometric implication. If you have 2 points on each side, that means this 2 point has to be almost antipodal, right? That means this 2 point has to be almost antipodal for the inner edges. And every pair of edges, one has to be in the hemisphere of another, right? But let's draw them on the same picture. The idea is that if you have 2 pair of antipodal points, if you put them together, I have to tilt a little bit for them a little bit closer to be adjacent. If you tilt a little bit, one pair is going to be too far to be on the hemisphere. Does it make sense? So you don't have K4. Okay, so finally I can get to the topic of today's talk, a generalized problem of this. Okay, so I have to tell you the result. Is there any question for K4 problem?
This adjacency is when you have distance bigger than 2 minus epsilon.
Right, this epsilon and epsilon prime you have to choose carefully. For one epsilon, you have to choose that this measure is 0. For the other hemisphere, you have to choose that this measure is 1/2, close to 1/2. So you have to choose carefully so the number add up.
Confusing about independence. What happens if you take 1/3 of
1/3 of a part. The number of vertices here is little o(n). Because let's imagine this. We take a very high dimensional sphere.
Yeah.
So Yeah, I forgot to write it down actually. I should have. Our vertex set is a unit sphere of dimension k, where k is really, really large. So how we think of it, you can think of the whole set. Let's think, imagine k really big, right? Then in the middle, most of the measure is here, right? If you take the top 1/3, the measure is 0. Yeah. Okay. So, in fact, the clique problem, I'm running out of time. So, the clique problem is resolved. So, let me write down the result. Early Schoch proving 70 that rho of k2s plus 1 is this. So, in particular, when s equal to 1, the triangle density is 0. Okay? The even clique problem is much harder, as we see, because of this, right? So eventually, the even problem is also resolved by Erdos, Heino, Schoch, Simonovich, and Samarady in '83. So they proved that this is this number. So when s equal to 2, that equals to 1/8. This number doesn't really matter. I will tell you why. How does this number come from? And then motivate today's problem. Today, what we want to talk about is the generalized, is the alpha p is the S independence number. So we define RTS exactly the same, except now I require the S independence number to be sublinear. What it means is that if you have a linear size subset of vertices, then you will see a KS. When s equal to 2, that's the original problem, right? This means, i.e., for any linear size set contains a copy of KS. Okay? I've been lazy here. Any question about this? So then we can similarly define rho S T. This is the density okay. You normalize it. You look at the Ramsey-Tura set density with respect to Ks. And you forbid KT. Well, again, let's do some exercise. This equal to 0, right? Why? So what we're doing now, we forbid K4. And every linear size set, you will see a triangle, right? Let me write K4 to not confuse you. In this graph, if you look at V, this is triangle free here. Because if you have a triangle, I get a K4, which is forbidden. But I know that any linear size set, you will see a triangle. That means the independence number, maximum degree is by alpha 3 of G, which is little of n, right? So this is very easy. But turns out this problem is very difficult. Because already, the next case, we have an upper bound 1/3, and lower bound 1/4, I believe. So there, 1/4, 1/8. I was supposed to double check on the box, but I didn't. So something like this. There is a gap. Let's put 1/8 to be more dramatic. Okay. So let's say there's a gap 1/8. 1/8. Maybe it's Maybe 1 over 4. So anyway, there's a gap here. We don't know the answer. Is the question clear? Again, you for big 5 click, every linear size set, alpha 3 of G equal to sublinear means if you look at big omega n of vertices, you will see a triangle. Okay? Then already this simplest case we cannot determine. This is trivial case. This case we cannot determine. Actually, for a while, we don't know if this is positive edge density. Then there's a construction a few years back showing that gave a lower bound 1 over 8. Okay, so let me mention now the 2 other major open problems. The other is to get Bollobas-Erdos graph So one of the tools we can do to get lower bound there is to use some sort of Bollobas-Erdos type graph with various other density. We've seen this graph here. You have an almost bipartite graph. The density is 1/2, right? So one of the major open problem in this field to attack this general problem for the lower bound is to ask, can you generalize this construction to get outer density? So for this, the known progress is that you can get a power of 2. Let's say I'm running out of letter Q, P. Okay? Density P, that's fine. So only for very specific density, the power of 2. So you can see here you get 1/2. And a few years back, Bollobas and Lenz, they take some product construction to get power of 2. Okay? So this is one of the major open problems. Can you get other density? If you can, there's a hope of closing the gap here. The second major open problem, the third, is that it's a very bold conjecture that extremal structure Okay, I stated quite informally, but let me just explain you what this means. But this one is clear, right? We want to get some sort of construction like this with density other than 1/2. Because of the lower bound there, for row 3, 5, say, the simplest case, we don't know how to do it. For the third one, what do they mean by this? This is conjecture by Erdos, Heino, the same author there, Schoch, Shumanovich, and Samardy in the 80s. Okay? So this problem basically says, we don't know how to do this problem, rho ST, let's make an even harder conjecture. Oftentimes you do it, right? You don't know how to do it, but you make it even harder. So what is the even harder problem? Let's start with understanding this. The original problem, where s equal to 2. The original problem, s equal to 2, you only require independence number to be sublinear. When t equal to 3, we know the edge density is 0, nothing to do there. So let's forbid k4, right? And we know for k4, I will always use red for density 1/2. So for K4, we know the Bollobas-Erdos graph gives us the tight bound 1 over 8, which looks like almost bipartite with density 1/2 going across. For K5, how do you do it? I will use white for density 1. So what we do is we put complete bipartite graph. Inside here, we put the high girth graph with independence number little o(n). Such graph exists by a probabilistic construction of Erdos. Remember, you can construct a graph that has high chromatic number and high girth. If you have high chromatic number, you have sublinear independence number. Okay? So you can stick this graph inside. High girth means this is triangle free. So you cannot have triangle here, you cannot have triangle here. The largest clique you can get is K4. So this is K5 free, sublinear independence number, edge density 1/4. And that's the right density. What about K6? You grow it. Now, I add one part. I have Bollobas-Erdos here. I add with density 1, attach a new part. Now, if you do the optimization, you get this number. So on and so forth. The next one, t equal to 7. You make this red becomes 1. And you put here the same graph inside. Okay? What's the next one? Let's draw one more just for fun. Always, you have a multi-part-type 1. Exactly one part, density 1/2. The other part is 1. Okay? Oh, t equal to 8. So in fact, what they prove here is something stronger. They proved not just this Turán density, they also proved that asymptotically, the extremal structure looked like this. If you forbid the even clique, exactly one pair has density 1/2 across, all the other is density 1. Okay? So now I can state their conjecture, this major problem. So their problem is saying that this phenomenon carries over to higher S, value of S. What do we mean by that? Let's start with a simple example. This means, let's consider S equal to 3. So that means every omega n set, you will see a triangle somewhere. Okay, that's what it means. Now, we know t equal to 4, there's nothing to do. It's 0 edge density. So the first case is t equal to 5. They conjecture that what you see, it should be 1/3 here. Did I erase? Remember before, I say that this is between 1/3 to 1/8, right? So they conjecture that this upper bound is tight. And it looks like this Bollobas-Erdos type graph with 1/3 density going across. But so far, all we have can construct is power of 2 by some product construction of the original ones. Okay, so this is and when t equal to 6, they conjecture that what now? You have 2/3 here. Okay, t equal to 7, then you put 1 here. This is fine because you can put the high girth here. You can do the same as this, right? So this is easy. Okay, so t equal to 8, as you imagine, we add one part attached to this. Does it make sense? And you keep going. T equal to 9, you change this to 2/3. Maybe I should use a different color to indicate the different density. Okay, the next one. And when you go over 9, you make them all by 1. So basically what they conjecture is that for the initial value, this is the initial value, this is the initial value, you always grow, if S equal to 2, you go from 1/S all the way to 1, right? So 1/S is 1/3, 2/S, 2/3, they grow to 1. After you reach 1 by part type, you attach a new part, start with 1/S between one pair, and start over again. This is the asymptotic structure. That's their conjecture. So I don't have much time. Let me just say our main result. Our main result is to resolve. We answer this question. Basically, we construct all Ramsey-Turán graph where the density is any rational up to 1/2. Okay? So this still leaves the question of constructing Bollobas-Erdos type graph of density above 1/2. But we can do for any rational less than 1/2. This is joint work with RST. Yeah. Okay, the first result is we can construct Bollobas-Erdos type let's say generalized with density A for any rational A up to 1/2. So in particular, one of the corollary is that this does equal to 1/3. Okay, for example, and many other values I'm not writing here. So we do know that this is true for the first one. Okay. Our second result is that this both conjecture about the extremal structure for the general RS problem, alpha S problem, is wrong. Okay, so the alpha S problem says what? Up until you go to t equal to 2s plus 1, the extremal structure is always almost bipartite. You go from 1 over s, 2 over s to 1, right? And then you attach new parts. This is the conjecture. But we managed to construct extremal graphs that's q partite for many value of q. There's a formula for infinitely many q for some parameter s and t. Okay, this I'm running out of time. I'm not going to write it. Basically, what we prove is that we get a construction that is tight, showing that not necessarily it look like this. Okay, you could have already when s is at most, when t is at most 2s plus 1. Their conjecture is saying you should grow always from 1 over s, 2 over s to 1, right? All the way to 1, and you keep attaching it. And we show that in this range already we see other extremal structure. This value is not even true, what we show. This conjecture value, we construct something even denser. I don't remember the numbers, but I can look it up later. But basically, we resolve the second and third problem here. Okay, so this is too bold. This is wrong. But for infinitely many cases, this is true because of our Ramsey-Turán construction. Okay, so one of the problems remain for these two major problems is, can you construct something denser, bigger than 1/2? This we do not know. So there's some problem. So let me just mention how we're going to do this. This is another construction, but for example, for this one, there, Bollobas-Erdos, we use the high dimensional sphere, right? You have the top and the bottom hemisphere measures 1/2. So for a while, we keep thinking, how do we get other than 1/2 if it's not hemisphere? Because if you step away from the equator, your measures quickly decrease to 0. So there's no 1/3. So what we do instead at the end is a natural thing that we missed at the beginning, is to take the complex high dimensional sphere. If you have the complex number, you can use the rotation to get any rational number. But the thing now is that when the rotation is bigger than 1/2, the region becomes not convex. Then you have a concave region, you take combinations, the point might fall out of the region that we want it to fall in. So things not working when it's bigger than 1/2, very roughly. Okay, I'm running out of time, so let me just stop here.